You zoomed in on the Dr. Pepper thing?
Oh, no. I was just trying to point it towards you.
Okay, that's a good thing.
Do you like Dr. Pepper or Mr. Pibb?
Wait.
Dr. Pepper.
Yeah, we need to get you that sponsorship.
Can you turn to the side so that we can see the logo? Because then they'll give us that. Yeah.
Hey,
Dr. Pepper.
maybe Dr. Pepper.
Sponsored by Berg.
Yeah, maybe they'll give you some money for the solar project.
Yeah, maybe they'll give you money for
Well,
the
honestly, I guarantee you could probably get some of Dr. Pepper. Because Dr. Pepper, like, gave Carol, like, Carol got, like, everyone from school got free Dr. Pepper because some kid DM'd them on Twitter.
Well, here's the problem, is that this is pretty much like a Coke-sponsored school. So you get into like a turf war with that.
Just don't tell them it.
Yeah.
They don't have to know.
Wait, if this is a Coke-sponsored school, Coke. Or ask the Coke brothers.
Okay, now, so let's chit-chat about what I want you to get out of this lab and why I wrote it. So, on the way up, everybody's cool. You realize you have positive velocity and you have negative acceleration, and everybody says, hey, cool, right? So, here's the ramp, right? Here's the cart. And you gave it some initial vertical velocity. So here's the main thing. What could possibly happen to that vector, that velocity vector, once it leaves your hand?
Speed up.
It can get bigger,
Stay the same.
Get small.
it can stay the same,
Get smaller.
it can get smaller. Okay, that's it. There's only three things that can happen. Now, so what did happen?
It got smaller.
It got smaller. So you're going to come in here on that second page and you're going to draw some velocity vectors. Here you go. Oh, here's V1. Okay. There's V2. There's V3. Okay? That's all you have to do. If you think they're getting bigger, draw them bigger. If you think they're getting smaller, draw them smaller. So here's one thing I want you to look at when I wrote this lab. Your acceleration vectors can only point in one of two directions. They either point in the same direction if your velocity vectors, or they point in the opposite direction if your velocity vectors. That's it. There's the only game in town. That's it. So which direction are your acceleration vectors going to point? Up or down?
Down.
Down. Okay. So you're going to come in here and say, okay, here's acceleration vector number 1. Now, here's where the wheels typically fall off. Okay? You typically get the velocity vectors right. Oh, they're getting smaller because you're slowing down. But what you're tempted to do is that you're tempted to draw smaller and smaller acceleration vectors because you're equating acceleration with velocity. Okay? You have to remember acceleration is the rate at which your velocity changes. So everybody says, well, it's slowing down. I'm not arguing that. Okay? I'm not arguing that it's slowing down. But your acceleration vectors have to stay the same, and here's the reason why. You look at F equals ma. What's creating the force to make this cart slow down?
Gravity.
Gravity. Is gravity a pretty constant force?
Yeah.
Yeah. Want an easy job, be the gravity forecaster for the world. Same as it was yesterday. Next. Okay, boom, there you go. Okay. Don't get the gravity app on your phone. Don't download it. It's not going to change. If it does, we're screwed. Something bad has happened. Or weird. Okay? So here's the deal. Your acceleration vector is going to point down, and they're going to have a positive or negative sign.
Negative.
Negative, because we're defining up as being positive, right? So you can say, oh, here's some negative acceleration. So this is one way I wanted you to see this. Okay, hey, the acceleration vector is pointing down. Now, here's what everybody wants to do. On the way down, you want to flip the acceleration and make it positive, because you associate positive acceleration with speeding up and negative acceleration with slowing down. But here's the problem. If you flip your acceleration vectors and point them up the hill, what have you said gravity has done?
Change.
Yeah, gravity flips over and starts acting up the hill when the cart rolls down, which would be exceptionally weird. Okay? Just unheard of. But that's what you all want to do. You want to flip your acceleration vectors and make them positive because you think, oh, positive acceleration means that I speed up. What's the only way that you can speed up with positive acceleration?
If positive velocity.
If your velocity is also positive. Well, guess what? Is your velocity positive going down the ramp?
No.
No, your velocity is negative going down the ramp. So guess what? Your acceleration still has to be negative. So you're going to have the exact same acceleration on the way up as you did on the way down. So that's one way that I want you to understand how this is going to happen. Here's the second thing. Your velocity time graph is going to look something like this. Okay? Now, one of the things you're going to do is you're going to calculate that acceleration. Now, Tori, when I look at your paper, when I look at those calculations, when you're finding this initial velocity, what do I want to see? I want to see units. So help me. You hear me right now. If all I see are random numbers with no units on it, I don't care. You have to understand, I am not concerned about the answer. I am concerned about the process. And if you just write down random numbers, oh, and then a miracle happens and it turns into meters per second or it turns into acceleration, I'm not buying it. Okay? I am not buying it. This is a process. It is not about writing down random numbers and then, oh, Burkamp wants velocity, so I'll put meters per second on the end of it. Okay? Part of your grade is the thoroughness of the units throughout the calculations. I want the process. I'm not worried about the product. The product will take care of itself. But unfortunately, I have to undo 12 years of your education where you focus on getting an answer that you can write down on that little space that I gave you on the right side. And you think that's the only thing that the teacher worries about. And that is true 99.9% of the time. I'm not like the 99.9. I worry about what's happening to the left more than I worry about what's happening on the right. Because if you don't understand what's going on, you've randomly written down numbers and you haven't shown me that you understand what's taking place. So, here's the second thing that you should see. Is that when you calculate that acceleration on the way up and on the way down, what should you get? A different value or the same value? Same value. Oh, that's kind of cool, right? So, you're going to look at this graph and you're going to go, oh, here's a velocity time graph. Wow, that thing has the same slope all the way. Oh, that's kind of cool, right? Because if you're going to change the slope of your velocity time graph, and this is true, if you think about this, what do you have to do to change the slope of a velocity time graph? Change the acceleration. What do you have to do to change the acceleration? F equals ma. Change the force. This is what you do when you drive, okay? When you press down on the gas pedal, you're applying a certain amount of force, right? When you hit the brakes, you're applying a different type of force. And that's going to create different accelerations. So you control the acceleration in your car by hitting the brakes or hitting the gas pedal. Do you barely hit the brakes? Do you stand on the brakes? Do you barely hit the gas pedal? Or you like the idiots that were taking off yesterday coming out of the parking lot and their hot rod cars with the really loud mufflers going, it's like you go, idiots. Anyway, I hope that was none of you. If it is, I don't apologize. So, anyway, so to change the slope of your acceleration graph, or excuse me, change the slope of your velocity time graph, you have to change the acceleration. To change the acceleration, you have to change the force. Well, since gravity is what's providing that force, that slope doesn't change. So that's the second way I want you to look at it. Here's the third way I want you to look at it. Is that this calculation of acceleration, A equals V minus V naught over time. Okay? You're going to calculate your accelerations this way twice. Once on the way up, once on the way down. You should see that you get the same acceleration. So when I wrote this lab, I want you to look at acceleration three ways. Graphically in terms of your vectors on here. The slope of your velocity time graph always being negative, and then this calculated value of acceleration. Okay? And you should see clearly reinforced that on all three of them, they're the same acceleration with the same sign, acting in the same direction because it's the same amount of force. Okay? Cool with this. Any questions? Now, let's talk about the last problem on the lab, where you throw the ball up in the air, it goes up for 5 meters and then comes back down for 5 meters. Here's how you can see if you did that right. So So your velocity time graph is going to look something like this, okay? Now, in big bold letters, I told you to write down the velocities on the velocity time graph, okay? Do that. So here's the kicker. If you want to know if this is right, come up here and find this velocity, okay? Find your velocity. Find the area of this rectangle, because you know the height of the rectangle, and you know the base of the rectangle. Find the area of this triangle right here. If you're right, what should the area of this triangle be? What's your maximum height? 5 meters. So if you take this velocity that you have written down times this base, and you take half of that and you get 5 meters, odds are you did it right. Not guaranteed, but odds are that you did it right. But I promise you, if you find the area of that triangle and it's not 5 meters, I promise you, you did it wrong. Okay? You did it wrong. Now, one of the things you've got to be able to do is take a process and apply it to a different situation. If you don't know how to do that last problem, go look at what you did on the previous page, where you took, oh, here's the displacement. Oh, that's the area of a triangle. Oh, that's 1/2 base times height. Oh, I know the base. I will find the height. Oh, I will calculate the acceleration. And so help me, if I don't see the work off to the left, bad things are going to happen. Okay? Any other questions? Once? Vonda? You sure?
I'm good, I'm good.
You're positive?
Yeah.
Okay. All right. So, once, twice sold, staple the graph to the back and hand that puppy in. So, but I talk the time.
Nice.
I'm okay with
I
that.
just love the
Dude, that's good news, good news.
Huh?
What are you talking about bad news?
Where's the bad news?
That is a win-win situation.
Well,
Bro, you're actually interesting.
Yeah, it's
As long as we
not,
take those group
it's
stretch
not
sessions,
funny.
we're good.
Like,
Yeah, for real, but like.
If you give us the stretch sessions,
I'll give you a stretch session.
we'll be okay with that.
Probably about 12:15. We'll have a stretch session. Okay? All right, that's good. All right,
Still got some.
we're ready to go. Okay, so what you need is your big dog equation sheet. And so when you look at your big dog equation sheet, there's 4 equations up there in the top left called the kinematic equations. There's 4 of them. And so those form the basis of all acceleration calculations. So what I'm going to do is basically today go through and show you where those equations come from and the hidden subtleties within those equations. Because if I don't do that and I just turn you loose and go, oh, here's these equations, it's a train wreck, okay? So I'm going to go through and kind of show you where those work, where they come from, when to use them, when not to use them. And then we'll finish this discussion tomorrow, and then you'll have your first real physics assignment tomorrow, okay? Yes, the first real one. You're going, what have we been doing so far? That's just been, leading up to the first real physics assignment. Yeah, it's going to be good. But you don't have that till tomorrow, so chill out. Okay. All right, so what you have first, man back, is that you've got this equation up there at the top. You have V equals V naught plus AT. Okay, the very first equation that's up there. Now, here's a couple of things that are important. First off, quick refresher. What's the difference between V and V naught?
Initial versus final.
V naught is the
Initial.
Now, how does, if you think about this in terms of a velocity time graph, all this is, if you look at this equation, all this is a slope-intercept form that you all have learned since Algebra 1. So all this is y equals b plus mx. Because what's the slope of a velocity time graph give you? Acceleration. Okay? What's graphed on your x-axis?
Time.
Time. This is going to be your y-intercept, which is going to be your initial velocity. So all that is a slope-intercept form. That's it. There's nothing else to it. That's all it is. So one of the things that you've got to be able to look at in terms of altering numbers and the impact that has, the beauty of this is that this is acceleration multiplied by time. Later on you'll see that we're going to take some accelerations and multiply them by time squared. Because this is just acceleration times time, that means this is going to be a linear function. If I multiply it by time squared, then it's going to be a quadratic function. So anytime you see acceleration times time, it's always a linear function, which means if I double the time, I double the change in my velocity, because it's just a straight linear relationship. Okay, so don't flip out on it. Okay, so all this is, here's your slope, that's your acceleration, you got your y-axis, you got your x-axis. That's it, okay? That's all there is to it. So, but one of the things you've got to be able to do is solve this equation for different variables. So let's say I give you this problem. All right, here's the famous carrot car, right? And the carrot car has an initial velocity of, I don't know, 4 meters per second. Bree, do you want the car to speed up or slow down?
Speed up.
Okay, so then later on we have a velocity of 12 meters per second, and let's say that that took, I don't know, 4 seconds. Okay, so I've got an initial velocity of 4, final velocity of 12 times 4 seconds. Now, here is the beauty of every acceleration problem. Every acceleration problem can only play out one of two ways, and one of two ways only. Either I'm going to make it speed up, or I'm going to make it slow down. Okay, that's it. That is it. Every acceleration problem that you have can only be one of two things. It's either speeding up, or it's slowing down. That's it. There is nothing else. Okay? Now, as soon as you know that Bree said, hey, this thing is going to speed up, as soon as I saw an initial velocity of 4 meters per second, what did I know the sign of my acceleration has to be?
Positive.
Positive. Literally. Ask yourself that question. Is it speeding up or is it slowing down? Those are your only two options. If it's speeding up, make your acceleration and velocity have the same sign. If they're slowing down, you know they have to have
Opposite.
and there's no exceptions to that rule. Literally, those are that's a two-trick pony. I either make it speed up or I make it slow down. Okay, that's it. That's it. So start with that basic idea. So, one of the things that you'll see, the more ways you can analyze a problem, the better you're really going to understand what's taking place on this here. So, here I've got 4 meters per second, right? So I'm here at 4 meters per second. That's my initial velocity. That's my y-intercept. That's all I'm saying is that this is my y-intercept. So my time out here is 4 seconds, and I end up here at 12 meters per second. Now, if I were to draw a series of velocity vectors, here's going to be my v1. If I draw a v2, what's going to happen to the magnitude of that velocity vector?
It's going to be bigger.
It's going to get bigger. Why? Because Bree said she wanted the car to speed up. Okay. So then V2 is going to be bigger, V3 is going to be even bigger. Okay? So which direction, Vonda, is my acceleration vector going to point?
Positive.
To the right or to the left?
Right.
To the right. Ah, cool. I'm going to have some positive acceleration vectors because my velocity vectors are getting bigger. Cool. There we go. Now, I also know that my velocity time graph has to slope up. Hunter, how do I know that my velocity time graph has to slope upwards?
Because your acceleration's positive.
Beautiful. And I'm going from 4 up to
12.
12. I can't go from 4 up to 12 with a negative acceleration. Okay? It ain't going to happen. Because you can't tell me, oh, I've got to have a line coming down like this, but I'm going to end up here. No. Okay? Not even in non-Euclidean geometry without work. No. Okay? It won't work. So everything has to fit together. Your acceleration vectors have to point in this direction. Your velocity time graph has to point in this direction. You know that's going to be your slope. Everything has to fit together. If anything doesn't fit, you have done something wrong. This all has to be a cohesive idea. Now, I know my initial velocity, my final velocity, and my time. I want to find my acceleration. So what am I asking you to find in terms of the slope? The value of it, right? I'm going to say, hey, what's the slope? That's your acceleration. Okay? Here we go. So if that's the case, I'm going to take this equation and I'm going to solve it for my acceleration, which is going to be the value of the slope. It's simple. Now, you are no longer freshmen in an Algebra 1 class. If you were, I wouldn't talk to you anyway. But you have to get in the habit of solving these equations for these variables. It is the most important thing that you can do. Okay? Do not plug in numbers and then solve it. It's going to be a train wreck. Okay? I promise you, I promise you, I promise you. I will never write numbers into the equation and then solve it. You know why? Because you're going to waste a whole bunch of time and you're not going to see how things fit together. This is about conveying to me how you solve a problem. It isn't about the answer, okay? I know I preached that, but it's true. So you can write this down and say, hey, this is what I'm going to start with, but I want to see this equation solved for acceleration. So, Felix, how am I going to get acceleration by itself?
Minus. Is it plus and then t?
Yeah, so it's v equals v naught plus at.
Oh yeah. Divide the t over.
Nope.
Subtract
yet.
the v naught.
Subtract your v naught. So we're going to have a equals v minus v naught, then what?
Divide t.
Divide by time. Okay, that's kind of cool, right? So this is what I expect to see. Because you're trying to convince me that Bergkamp, hey, I'm running with big dogs now, I can solve an equation. And here's the reason why. Because eventually, like especially when we get into like gravitational calculations, mass of the Earth is 5.979 times 10 to the 24th kilograms. It's much easier to write m sub e for the mass of the Earth and solve an equation than it is to write 5.979 times 10 to the 24th kilograms. This is how science is done. It's not Algebra 1, okay? Get over it. Don't write down the numbers and then solve it. Stop, okay? Now, once I get here, what I'm going to do is wrong. Do not do what I'm going to do. So I'm going to sit there and go, okay, final velocity, oh, that's 12. Initial velocity, oh, that's 4. Time is 4. 12 minus 4. That's 8. 8 divided by 4, that's 2. Bergkamp wants an acceleration, so I'll put meters per second squared. Now, why am I not going to be happy with this, Tori? Because there's no units. I don't know what you've done. You took 12 minus 4. Big whoop. 12 what? 12 squirrels minus 4 chickens? I don't know what you did. And then you divided it by the number of penguins on an iceberg. I don't know what you did. Okay? I don't. You have to pay attention to the units. And literally, the sooner that you embrace this idea of paying attention to the units and working this as a holistic problem, the better off you're going to be. Now, you can wait until you're done with physics and then go, wow, Bergkamp was right. I should have paid attention to the units all the way. Okay, you can wait to the end. You're going to waste a lot of time and you're going to get really, really frustrated. Or you can embrace it now and go, wow, maybe that old man in the front of the room that's wearing a tie actually knows what he's talking about. I'm just going to throw that out. At some point you might come to that conclusion. I don't know. But literally, if you look at my answer keys, when I work these problems, this is what I don't do. Okay? If you look at my answer keys, I've got units on everything. Okay? I just don't randomly write down the numbers. I put the units on everything because it's the process. Okay? I've done this longer than you all have even thought about being on this earth. And I still do this because it works. It eliminates the problem. Now, when I take meters per second and divide it by seconds, what do I get? Meters per second squared. Is that what I want for acceleration?
Yes.
Yes. Okay? So, throw in correct number of significant digits. There's my acceleration. Now, here's how some people like to think about acceleration. Some people like to think about this in terms of money. Okay? So stay with me here. What we're saying here is that you walk into the house and you have $4 in your pocket. Okay? Mom goes, wow, looks like you've had a rough day. What this means is that for every second that goes by, your mom is going to give you $2. Okay? That's what that means. That's what that acceleration function means. So, if you start with $4 and mom gives you $2 per second, at the end of 1 second, how much money do you have? 6. Oh, welcome to the world of acceleration, right? Another second's going to go by, you're going to have 8. Then you're going to have, how long does it take you to go from $4 to $12 if mom's giving you $2 per second?
4 seconds.
4 seconds. Welcome to acceleration. That's what that number means. So when you look at this acceleration of 2 meters per second squared, that's the rate that your bank account is going up per second. Okay? That's all that means. It doesn't tell you how much money that you have. This just tells you the rate at which your bank account changes. Go with that. Okay. Now, you can do this a little bit differently. You could say, okay, here's the carrot car. It's got an initial velocity that I don't know. The car is going to slow down to 12 meters per second at an acceleration of -4 meters per second squared. And let's say that took, Felix, click number between 5 and 10. 7 seconds. Okay? So, I don't know how fast the car is going, but I know that 7 seconds later, with an acceleration of -4 meters per second squared, I know that this car is going 12 meters per second. Okay? I want to know how fast it was going at the beginning. All right? So, here's the dumbest thing that you can do. The dumbest thing that you can do is go to that big dog equation sheet and go, oh, which equation am I going to pick? Oh, no, don't, stop! Draw your velocity time graph first. Roughly. Great. What's this velocity time graph going to look like?
Acceleration, it'll be a negative.
So I'm going to start high, go low, or start low and go high?
Start high and go low.
Start high and go low. Kind of the Colorado thing. Okay. So, it's true, don't act like it's not. Okay. So I'm going to start with some positive velocity, right?
Yeah.
And it's going to go down like this. Curved line, straight line.
I'm going to assume the acceleration's constant, so straight
Or
line.
uniform, yeah.
Okay, so straight line.
Straight line,
Yeah.
okay. And what's the slope of that line?
-4 meters per second squared.
-4 meters per second squared. I like that. Where do you end up?
At
12?
yeah, 12. Sorry.
So here's the deal. Before you even tackle this problem, okay? Before you even tackle this problem, Olivia, is my answer when I get how fast this thing was going at the beginning, is my answer going to be bigger or smaller than 12 meters per second?
Bigger.
Why? You're right.
Your initial velocity was above 12 meters per second.
Yeah. Okay. If I get a velocity of like -12 or like a negative number, I have done something horribly wrong. I can't go from a negative velocity up to this point with a negative sloping line. It doesn't work. Non-Euclidean geometry doesn't make any difference. It's not going to work. So before I even tackle the problem, I know that this number up there has to be a positive number that's bigger than 12. If I don't get that answer, I've done something wrong. Okay? That's it. So this is what I'm searching for. So, right now we only have one trick pony, and that's V equals V naught plus AT. At the end of the day, what am I searching for in terms of this graph?
V naught.
Yeah, the y-intercept, right? I'm trying to find the y-intercept. That's what I'm searching for. So, how am I going to get V naught by itself? Logan, what am I going to do?
Subtract V naught and then divide by 2.
Hold on. I want to get V naught by itself.
Oh, you want to get V naught by?
I want to get V naught by itself.
Okay, then subtract 8.
Beautiful. So I'm just going to go V minus at equals vo. Okay, there we go. Now what can I do? Now I can put in the numbers, okay? Because now I've got my solved equation.
But with
Oh,
units.
right, okay? So my final velocity we said was
Units are
12 meters.
12 meters per second. Now this is where you have to pay attention to the negative signs, because this is what you're going to do wrong. You mark my words. I'm going to do what I'm going to do. Do not do what I'm about to do. Do not do this. You go, oh, 12, I got an acceleration of 4 meters per second squared. Oh, look at me, I can physics. Felix picked a time of 7 seconds. So I'm going to take 12, 4 times 7 is 28, 12 minus 28, and that's what I'm going to do. So, what's the problem with this? If you take 12 minus 28,
get a negative number.
you're going to get a negative velocity. So, you're going to tell me that you're going to start here. I'm going to have a negative slope, but I'm going to end up here. Okay? It's the biggest thing you're going to do wrong, because you don't pay attention to the little things. But, here's where the miracle of math happens. This acceleration is actually a negative number. Oh, that's kind of cool. Now I have 12 minus a negative 28, which means and now I get
40.
40, right? Because this is 12 plus 28, and I get 40. Okay? Now, here's the beauty of physics, if you're willing to take the time. How can you see if you're right?
You know you're right because they have opposite signs.
We'll do the height thing.
What is this?
The height thing.
Do the height thing.
Yeah, the height thing, right? Can you do that? The base side of the triangle.
Well, look at it this
Oh wait, no,
way.
you can't. Never.
Use your numbers again.
You can think of it this way.
I'm dumb.
You can think of it this way. You're starting with $40. Okay, that's what you're starting with. Every second that goes by, how much money do you lose? $4, right? So if you start with 40, 7 seconds later, how much money are you going to lose? 28. So if I take 40 and subtract 28, I get, voila, here we go. I did it right. Okay? So that's how you can always check that you got this. Okay? So it takes a little bit of dare I say, effort. Okay? I said the E word, effort. Okay? Just a little. But if you're willing to take the time, number one, you can look and go, wow, does this fit with the model? Did I get an answer that seems reasonable? And then if I work backwards, is there a way that I can verify that this answer is right? And if you can, odds are you did it right. If you didn't, oh, something bad has happened. Okay? All right, so stop that, stand up, take a stretch.
I said to
Some of it can actually be like considered cheating.
Don't
really?
I haven't done it.
Pumpkin,
That's like
No! No way!
he said he doesn't want
For
A pumpkin is a squash.
no.
that's a game for sure.
So you sounded like sorry.
Did you mock him, Haley?
Huh?
Did you mock him?
Yeah, because he was like, no.
Haley, do you ever eat your granny pie?
Get him.
That's what I thought.
Okay, are we going?
Yeah.
Okay.
Did you, Carson?
All right, so now we need to come up with the second equation. Now, so let's look at this. We got a velocity time graph, and we have V naught, and then we have V, we can measure time. So if you go back to the lab that you all did yesterday, there are certain physical quantities that are pretty easy to measure. Distance. Okay, hey, where did the cart start? Where did the cart stop? That's pretty simple. Time. Not difficult to measure. Start, stop. Pretty simple. Velocity is a little dodgy, especially when you have accelerated motion because the velocity is always changing. But we worked out a way yesterday to calculate that velocity because using the triangle we found the height, right? And then once you get that, then you can calculate acceleration. It's exceptionally difficult to directly measure acceleration. Okay? There's some techniques you can use. But as far as like actually like aiming a gun at something and going, oh, what's the acceleration? Okay? You can't do it. But we can measure mass, we can measure time, we can measure distance. Then we're going to use those values to come up with some different quantities. But acceleration especially is difficult to measure directly. So we look at the changes in velocity, we use that to determine acceleration. So, with that said, so here's the velocity time graph. You're going from V naught up to time. So how could I use this velocity time graph to determine the displacement of the object?
Find the area.
Don't make this
Find
difficult.
the area.
Find the area, right? What's the area of a velocity time graph give you? Displacement. Okay, that's kind of cool. So, what I want to do is I want to break this up into two parts. I want to break it up into an area 1, which is the rectangle. And then I want to break it up into area 2, which is the triangle. Okay? Pretty simple. So, Garrett, how can I find the area of that lower rectangle?
Take the length and the width.
Beautiful. That one's pretty simple, right? That's just going to be V naught times time. All I'm doing is finding the area of a rectangle by multiplying velocity times time. That one's simple. This gets a little bit more complicated though. First off, it's going to look like a
Right.
triangle. So I know I'm going to have 1/2 base times height. So Honus, how can I find the height?
You can take 2a divided by b.
I don't know the area.
Oh, you don't know
I'm
the
trying
area.
to find the area.
Okay. So you're trying to. So what are you trying to find? So you're trying to find the area,
I'm
right?
trying to find the area. I need the
Okay.
base and I need the height.
Okay. Well, your base is going to be the same as what it was for the other rectangle.
You speak words of truth. Okay? Start calling you same base.
And then your height is going to be your velocity minus your initial velocity, right?
V minus V naught.
Yeah.
Why?
Because
You're right, but why are you right?
the triangle's the base of it starts right at v naught,
Yeah.
and then at the top of it's at v. So in order to find the height, you have to subtract those two because you're not starting at 0.
Ah, nice.
Thank you.
Nice.
Thank
Or physics class, I should say. So here's the deal. So look at it this way. Let's say this was 20 meters per second and this was 5 meters per second. The height of that triangle would be 15. So it's V minus V naught. So at this point, my total displacement is going to be this lower rectangle, which sorry. Are we good?
Soccer
Yeah, we're
players,
good now.
Of course.
Okay. And then I'm going to have 1/2 times time times V minus V naught. So one of the things you'll see, and this is going to sound strange until you do enough of them, but a good equation always has like a certain elegance to it, okay? Certain simplicity. So do you think that's a very elegant, simple equation?
Not in the slightest.
Oh no, this is like the ugly duckling of equations, okay? This is a train wreck. Okay, it really is a train wreck. So, but what I want to do is I want to get it so I can combine some terms. So like I want to distribute the 1/2 time over all of this. So I got V naught T plus 1/2 VT minus 1/2 V naught T. Okay? Now, can I simplify anything in here?
You can take a 1/2
Well, can I
t
take
from
V naught
V
t and
naught.
subtract a 1/2 V naught t?
Yes.
I can, right? And so what am I going to get? 1/2 V naught. So, if I take this and do a little shake and bake voodoo on the algebra side, so I take V naught t minus 1/2 V naught t, I get, whoa, flips me out every time it does. Hold on. There. So I've got 1/2 V naught t plus 1/2 VT equals distance. Now, at this point, I want to factor out a 1/2, because that's common. I don't want to factor out a time. So, what I'm going to get here, whoa, that's not what I want. I have no idea what that put an X on. Yeah, right. No, the circle won't go away. Okay. Weird, it's possessed. See, you even talk about Halloween, my board becomes possessed. So, I know some serious African traditional healers that curse on you. So, or remind me to tell you some stories about African traditional healers.
I'd love to hear those.
Okay.
Please.
No, not right now. Just at some point, remind me to tell you about Benny and the chicken. So
Benny.
Benny and the chicken.
Benny got turned into a chicken?
No. Just at some point, just say, hey, Burkham, tell us the story of Benny and the chicken.
How many masters of voodoo have you met?
Oh, like about 4.
Awesome.
Benny was the best, though. All right.
And then he
Okay.
ripped off the chicken's head.
So, this is the second equation that's on your sheet, okay? Now, you look at this and go, oh, what's the big deal? First off, understand where this comes from in terms of this is a velocity time graph. Now, this is what you all tend to screw up. This is a plus sign, okay? For whatever reason, you all try to subtract this, okay? You've got to add these together. Now, let me show you how this works. So, in general, we're going to have two types of motion. We're going to have constant velocity, and then we're going to have accelerated motion. Okay? That's what we've got. Now, here's what I want you to look at. What's the only situation, what is the only situation you can use this equation? Constant velocity. This is a one-trick pony. It's a good trick, but it's a one-trick pony. Y'all been using this equation probably since 5th or 6th grade. So this is constant velocity. So here's the setup. Let's say that you've got a velocity time graph that looks like this. Say you're at 4 meters per second, and then you're up here at 12 meters per second, right? And you know this is going to be like, I don't know, 2 seconds. So first off, did you accelerate?
Yes.
How do you know?
Your velocity is
Velocity
changing.
changed, right? Did I speed up or slow down?
Speed up.
How do you know?
Positive slope.
Well, one thing you can look at, Burkamp, tough question. You went from 4 to 12. You probably sped up, okay? Also, you have positive acceleration with
Positive velocity.
positive velocity. You're also going away from 0 meters per second. Okay, that's the other way that you can look at it, right? Okay. Now, there's a couple of ways that you can determine the displacement. I want to know how far this car went. This is a personal preference thing. There's 3 ways that you can do this. I don't care. One option is you go, Mr. Burkamp, man, I like geometry. Okay, good, cool, right? So, you can come in here and you take 4 meters per second times 2 seconds, and that's going to get you 8 meters. Now, is that your final answer? No. Why can't you use velocity times time and take 4 meters per second and multiply that by 2 seconds to go 8 meters and we're done? Why can't you do that? It would be so simple.
It's not constant velocity.
Yeah. Do you have 4 meters per second the entire time? No. You're going to go from 4 to 4.5 to 5.1732 to 8.2 to 9.99 to 12.0. This velocity is continuously changing. Because this velocity is continuously changing, I can't do this. So one option, though, you can take 4 times 2 and get 8 meters. Then you could find the area of this rectangle and you could add the 2 numbers together. If you like that, go with it. It's a little bit extra work, but if it fits with how you like to do problems, great, do it, knock yourself out. But then you go, well, Mr. Burkamp, I like statistics. Okay, all right, you like statistics. Happy for you. By the way, so let's say that you've got 2 velocities, a 12 and a 4. And I said, find the average velocity. What would you do?
Normally, you would add 2 and divide by 2.
Add them together and divide by 2, right? Okay, true? So you take 12 meters per second, add that to 4 meters per second, right? And divide that by 2. You take 12 plus 4, you get 16. 16 divided by 2, you get 8. So would you agree that that's the average velocity? Good? Average velocity. That's like the midpoint here at 8 meters per second. So then you go, wow, if this is my average velocity, which is 8 meters per second, then I can come over here and go, oh, Mr. Burkamp, look, I can do this. This is cool, right? So I like statistics. Good. Happy for you. What are the odds that you're going to get a date to prom? 0. That was rude. Okay. It's fine. It's like, yeah, don't use that as your promposal. What are the odds that you'll go to prom with me? Okay. Somebody you're on the use that, aren't you? Okay. What are the odds? All right. So once you get the average velocity, then you can go up here and go, oh, but look, Mr. Burkamp, I can take the average velocity and multiply that by time and find it that way. Oh, that you can use, but only if you use the average velocity. So look what happens, though. You're going to add the 2 velocities together, you're going to divide by 2, and then you're going to multiply that by time. Oh, right. Okay? So this is if you like probability or odds. Okay? Now, the other thing you go, Mr. Burkamp, I like equations. We have this really cool equation sheet. Oh, you're right, you do. And you go, oh, distance equals 1/2 v plus v naught times time. Look what happens. Right. You can take v plus v naught and you're going to divide by 2. Otherwise known as finding the average velocity. Ah, right. Then you take the average velocity, you're going to multiply that by time. Guess what? It's the same thing. Okay? It's the same thing. Okay? So, I don't care how you understand it. I don't care if you like rectangles and triangles, fine. Knock yourselves out. Okay? Yeah, like Mr. Burkamp, I go home and I find areas of triangles. That's my hobby. Good. If you develop that out, the area of a triangle out, you know, they just randomly give you the dimensions and you have to find it out. Okay. Anyway. Or you can find the average and multiply it by the time, or you can look at this equation. I don't care, okay? Literally, I don't care. Just find something that makes sense to you. Now, here's the $1 million question, amongst many $1 million questions. Let's say that you've got a velocity time graph that looks like this. You're at 8 meters per second for 6 seconds, okay? Could I use this equation to determine how far you're going to go?
Yeah.
You have a constant velocity.
Yes.
You know the time.
Yes.
All day long, right? So you're going to get 48 meters. That's kind of cool. Old school, you're finding the area of a rectangle. Simple, right? Length times width. Simple. But here's the question. Could I still use this equation?
Yeah.
Why?
Well, because your initial and your final are the same, so when you add them together and divide by 2, you get exactly 8 again.
I can use this equation even with constant velocity, because it's exactly what Hona said. If I take 8 plus 8, I get
16.
16 divided by 2 gives me
8.
8 times 6 gives me 48 meters. So this equation here works all the time, even with constant velocity. This is a one-trick pony that only works with constant velocity. So you can always use this one, but you can only use this one if you specifically have constant velocity. So this is like more of like the Swiss Army knife, because you can do more things with it. You can use it with constant velocity and accelerated motion. Doesn't make any difference. Okay, got that. All right, we're in the home stretch. Stand up, take the last stretch, and then we're Boston Red Sox.
Yeah.
And he's just is not good.
There's a few.
Okay, all right. Okay. Enough fishing clubs.
Are you a big fisher, Bird?
I used to be when I was in high school. I'm not anymore. Okay.
Show you.
Oh, that wouldn't take much. Okay. So now we're going to do a little bit of voodoo. Okay? So here are the two equations that we've come up with so far. So what I want to do next is I want to take this equation here. Usually that doesn't elicit that many laughs. Okay? I want to take this equation here and substitute that in here for this v. Legal?
Yes.
Yeah.
Yeah, because if this equals v and that equals v, I can substitute that in. So I got distance equals 1/2. Then I'll take this whole thing, v naught plus at. I've still got this v naught that's still in there, and multiply that by time. So we're going to live on the edge, okay, but I think we can do this. At the same time, I want to combine everything that I can in here, distribute the 1/2, but yet, wait, there's more. I want to distribute the time as well. Oh, I know, serious algebra voodoo. Okay, so if I take v naught plus v naught, I get
2v naught.
2v naught or not 2v naught. In this case, I get 2v naught. Shakespeare meets Isaac Newton. Okay, so I've got 2v naught, but I want to multiply by 1/2, so that knocks me back to
V naught.
a v naught. But then I'm going to multiply by time, so I'm going to get
V naught.
v naught t. Wow, that was complicated. Okay.
Naughty.
V naughty, actually.
Yeah, very naughty.
Very
Bring that finger.
But it's not v naughty squared. That would be bad. Okay. Okay. So I got these taken care of. Limited or consolidated or v naughts. So then I got 1/2 times at times t gets me
8t squared.
1/2 at squared
Yeah. So you're back in the inside.
plus v dot t.
Dude, that's
So
not
welcome
pre-con.
to
It's
the third equation on your equation sheet. Okay. So all I did was I took these two equations, combined them into this. Now, what's the one variable that's missing from this equation that's in the other ones?
Oh,
B.
V final.
Final velocity, right? Okay. This is not dependent upon final velocity. The other ones are. So if you're trying to find like if you're trying to say, hey, you know, a proton is accelerated from rest over a certain time, what's the final velocity? Don't pick this equation, because it doesn't involve final velocity. Now, there's an interesting thing that happens. What if you have a carrot car that's driving along at a constant velocity of, say, 10 meters per second? and it's going to go with that for 5 seconds. Could you still use this equation to find how far it's going to go?
Yeah, because v is v naught.
Yes. Why?
Because v is v naught since there's constant velocity.
Well, if you're traveling at a constant velocity, what's the value of your acceleration?
Constant is nothing.
There is no acceleration, right? You have no acceleration. You're driving at a constant velocity. This whole thing drops out. What are you left with?
v equals vt.
Distance equals velocity times time. Okay? So this equation even works with accelerated motion. But if there is no acceleration, you just have distance equals velocity times time.
So does that top equation, if you use v equals v naught plus at, and acceleration is 0, then there's also no...
Yeah, if there's no acceleration, guess what? Your final is the same as your initial. And then you have a horizontal line on your velocity time graph, because then there's no slope. Okay? All right, so let's talk about this. Here's one of the most important things I want to point out right from the get-go. Notice here that you have time squared, okay? You have time squared here, multiplied by acceleration. Here, this is just acceleration multiplied by time. So with this one, if you double the time because it's squared, your displacement is going to go up by a factor of 4, okay? Because it's time squared. So this will produce a quadratic equation. Up there, when you just have acceleration times time, guess what? That's going to produce a linear function. So what that means is anytime you see acceleration times time, it's always just a linear function. This one, you have acceleration times time squared, that will always produce a quadratic function. So that's one of the most important things that you need to begin to look at when you look at equations. Focus on what values are squared, cubed, things like that. Because changes to those make a huge difference. I'm not saying that, you know, if I double the time, that is going to impact my velocity. But if I double the time here, that's going to get like a 4-time increase in my distance. So focus on things that are squared or cubed. Those produce completely different graphs than if it's just acceleration times time. So here's how you could use this. Let's say that you've got your basic carrot car, okay, and it's going to start at rest, okay, let's make it simple, and it's going to accelerate for, I don't know, 20 meters, and that's going to have a typical car is accelerated about 5 meters per second squared. So I want to know how long it's going to take. So here's the story. I got a car that's at rest. It's going to speed up 5 meters per second squared. It's going to travel 20 meters. I want to know how long this thing is going to take. So, do you know the final velocity? New. Okay, so right away you go, oh, I don't know the final velocity, nor do I know the time. So I don't know the final velocity, nor do I know the time. So I have 2 unknowns at this point. Okay? So now you got to go, oh, how is this going to play out? But again, look at this. What's that velocity time graph going to look like? Olivia, where is that velocity time graph going to start?
At 0.
What's it going to do then?
It's going to go up.
It's going to slope up like this, right? Straight sloping line or a curved line?
Straight.
Why?
Because acceleration is increasing.
Because acceleration is what?
Increasing.
No, it's not. Because if my acceleration was increasing, this would be a curved line.
Oh, because acceleration is staying the same.
Ah, there you go. You have uniform acceleration, right? So this is 4 meters per second squared. Is that the length of my hypotenuse? No, it's not. That's just the slope of the line. Okay, that is not the length of the hypotenuse. All that is the slope of the line. Okay. Now, how does this 20 meters play into this graph?
What's the acceleration from?
How does that 20 meters play a part? Yeah, that 20 meters is this area here, right? That's what that represents. But I don't know the final velocity. and I don't know the time. But here's what I want to do. I want to try and figure out that time. Well, look, you know, distance equals 1/2 at squared plus v naught time. True? What's my initial velocity? 0. Now, every problem that you're going to have is going to be a story problem. If you hate story problems, this is not for you. Okay? Because I will say, hey, a car starts from rest. And what you see is a lot of times either the object starts from rest and speeds up, or it's traveling and it slows down to stop. So a lot of times either your final or your initial velocity is going to be 0. So I don't have to, this is the international sign for that goes to 0. So how can I get time by itself? Nick, how can I get time by itself? I hate fractions.
Get rid of the fraction first by multiplying by the reciprocal.
Otherwise known as
2.
2. Okay. How about just we multiply by 2? Okay. So then I got 2d, then what?
You would have to get rid of the squared.
No. I'll do that later. I gotta get time by itself first.
Oh, you have a with, okay. So you have to get rid of the a, so divide by a.
Divide by a, and then do what?
Square it.
Then I can take the square root, then I can get time. So now, at this point, I can go, oh, okay, well, that's simple. I got 2 times 20 meters divided by 5 meters per second squared. Do I get the correct units out of this deal? Because I got meters divided by meters per second squared, so I end up with second squared, and the square root of second squared is, that's cool. So 2 times 20 gives me 40 divided by 5 gives me, square root of 8 is roughly, 3 would give me 9, 2 point something. Okay, so 2 and some change, right? So in other words, that's going to take 2 and some change seconds to go from 0, travel 20 meters at an acceleration of 5 meters per second squared. Okay, so that's how it plays out. So tomorrow we will do some more stuff with this. I'll introduce that last equation, and then you can go back to your first big physics assignment.
I would actually